Alright, so we're ready for the next section in our kinematics unit, is on vector quantities. So our outcomes, there's a couple in this one. You can use vectors to show displacement, velocity, and acceleration. And then you can also use math to see the connections between displacement in time and velocity. So vector quantities, there's some terminology to know, similar to the last unit that we went through when we were dealing with speed. And so our vector quantities, using our little Despicable Me vector guy here, some quantities that you're going to need to know. A vector quantity is defined as an amount of time, an amount that has both magnitude and direction. So, for instance, it's 34 meters per second and it's heading west. Anytime it has a number with it, with a unit, so it's saying what it is, and then it's also saying where it's going. It has a direction as well. We also have position, the distance and direction of an object from a given reference point. So that's saying like where something is normally from zero or a zero marker. And then we also have displacement, which is a change in position of an object in any given direction. So how much did that object change from where it was going from before? Okay, so I would encourage that you kind of know each of the terms and just kind of what they stand for if you want to jot them down in your book to have, or if you've printed off the slides, then to go through and make sure that you understand each one. So a common vector quantity we tend to talk about is displacement. Displacement is really distance, but it has this arrow above it. We've used this D term already to talk about distance. So when we talk about vectors, vectors are shown with an arrow above the term. So displacement is going to look like that D with a line on the top. And really, if we think about vectors and we think about distance versus displacement, the only difference really is that distance is telling you how far you traveled, whereas displacement is telling you two things. It's saying how far you traveled, but it's also saying in what direction. So, for example, a baseball player may run a certain distance to catch a fly ball. So if we knew the distance that was covered, then we could write out his displacement. And so the notation for that, for this diving catch, would be that this person runs about 10 meters right, and you can see that I have a D with a line over top. I've got my number, how far they're going, with a unit, and then I have these square brackets that denote the direction that they're moving in. So our next one, a triangle is something else that gets added in. And triangle just means change in. It's a Greek symbol. So placed in front of the displacement to show the change between two given displacements. So there is some kind of extra things that we can consider about this later on, but for now, we're just going to just kind of take this easy. So say we have a curling rock and it leaves a curler's hand at a point 9.2 meters from the starting point. So picture, as in the video here, this person pushes off the wall and they go 9.2 meters from the starting point. And that's when they tend to release the rock. So really from our reference point, the point of release is 0. They travel southward, as the rock does, and then it says what is its displacement from its original point of release after it slid to a point of 32 meters from the same edge. So it wants to know how far did the rock travel. Well, we know, common sense would tell us, really, we just need to subtract these two values, right? It was released at 9.2 meters, and it traveled a total of 32 meters, both referenced from the same edge. So our displacement here, we could write out, using our terminology that I've just shown you, we've got our change in displacement is really just taking a look at 32 meters, and we're going to subtract the 9.2 meters that it traveled. And so our change in displacement here is really 22.8 meters. Now this also needs a direction, so it's 22.8 meters heading south. Right? So we can show displacement and we can calculate displacement as well, just using some common reference points. Now, there's some extra terminology with this because, I'll just make this full screen. So because vectors imply direction, they indicate when a value should be a negative or a positive. So similar to how we see a Cartesian plane, we normally consider east and north to be our positive values, and similarly we consider west and south or left and down to be our negative values. And we're going to carry that forward in this course as well. So whenever we see something that's east and north, we kind of consider it as being a positive value, and when we see something that's west and south, we consider that to be a negative value. So kind of use that mindset of Cartesian plane as we think about vector quantities. Now, vectors can also be drawn to scale, and if you have a ruler, I would encourage that you try this out and just see how close you are to calculating it. As well, I do have rulers that are in my room that you're welcome to use, and we'll just have to make sure that we take care of those. So, example, we've got two players are playing badminton. One player serves a birdie a distance of 4.2 meters east, and then it's returned by the other player a distance of 7.1 meters west. So, what's the overall displacement of the birdie? So, try it out, pause the video, draw it with a ruler, and see if you can come up with the correct answer. So we'll go through the math of it here, I'll draw what it looks like, and just kind of see how you do. So, this thing starts off, if you can kind of picture a reference point here, it starts off and it says that it travels 4.2 meters east. So picture that it's starting at a certain point, and then it's traveling 4.2 meters. Now hopefully when you drew that out, obviously you're not going to use a meter stick. Hopefully you use centimeters to represent your meters, and so 1 centimeter would equal 1 meter. And you could draw this thing out to scale, right? 4.2 centimeters would be the same as 4.2 meters drawn to scale. And it's heading in the right direction. Notice my right arrow, it's heading east, just like we did with our Cartesian plane. Now it says after that the player then returns it 7.1 meters west. So that's a new line, but it has to start at the end of this reference point. So it's then traveling 7.1 meters in the opposite direction. So you could take a ruler and you can measure this out to be 7.1 centimeters. Almost wrote centimeters there. 7.1 centimeters long would be 7.1 meters. And then what we can see when we take a look at our vector, the vector problem doesn't really care about how you got there, it just wants to know straight start to finish. So really what we're considered with is our starting spot right over to the end. What is this value? And so if you measure that with your ruler, keep that term aside, hang on to it, and mathematically we can show what this is going to be. So we can set up a little bit of a formula for this. So our change in displacement is all of the different displacements added together. So displacement 1 plus displacement 2 in this case. So really our displacement here, displacement 1 works out to be 4.2 meters east, plus displacement 2, which works out to be 7.1 meters west. And then our change in displacement, I'm now going to get rid of the direction, and wherever I have a west and a south, I'm going to put my negatives in. So 4.2 meters, positive value, it's heading east, plus, and then I've got a negative 7.1 meters because it's heading west. So I know that I need to subtract these two terms. 4.2 minus 7.1 is going to give me negative 2.9 meters. So really, what does that negative tell you? Well, that negative, remember, tells you the direction. It's saying it's going 2.9 meters west. Significant digits, when you add, remember you go by place value. They're both in the tenths place, so my answer is in the tenths place as a final answer. Okay, so if you measure out our dotted line over here and measure yours on your page, hopefully you get something along the lines that's really close to 2.9 centimeters. That would kind of tell you that you're on the right track. We can also take a look at average velocity. So average velocity is different than average speed because velocity is a vector quantity, meaning it has a magnitude and a direction. So the same way we thought about displacement and distance, we need to think about velocity and speed also representing the same variable, but one is a vector, whereas one's just a scalar quantity. So our vector quantity has a line over the top of it. As you can see, it's still the same formula, still the same triangle, it's used all the same way. Just when you see the arrow over the top, that represents velocity. If you don't see the arrow over the top, that represents speed. And same thing with distance. If you see the arrow over the top, it represents displacement. And if you do not see the arrow over the top, then it represents distance. So when calculating average speed, we use the total distance that's traveled. That's going to be really important later. So speed wants to take into consideration all of the distance that has been traveled. When we find the average velocity, we only use the displacement. Okay, so we only use from start direct to finish. So that dotted black line from the last question, that would be our displacement. Okay, how far it traveled. So we can kind of see velocity problems with this as well in a similar kind of way. So just world's fastest coconut tree climber in 2017 is George Johnny Iona. It takes him only 5.62 seconds to climb barefoot 8 meters up a coconut tree, which is pretty crazy. The question then asks to calculate Johnny's average velocity for this motion, assuming that the climb was vertically upward. So we assume that he's moving vertically up the coconut tree. So pause the problem, give it a try, see if you can figure it out. Write out your formula, show your work, conclude your steps, and we'll go over the answer. Alright, so average velocity is displacement over time, which means average velocity is equal to 8.00 meters over top of 5.62 seconds. And we can find out that our average velocity is going to work out to be 1.4234 meters per second. And then if after that we took significant digits into consideration, looks like there's 3 in each one, so it looks like average velocity is going to equal 1.42 meters per second. And now I need a direction because this thing's a vector, and our direction in this case, we really don't have an east, north, southwest kind of direction, but we knew that it was vertically up. You just have to say where it's going. So using that information, you should be okay to start the next assignment. And good luck.